Hi, I'm Jackie, and I conducted a literary review on how HMIs, external human-machine interfaces, can facilitate interactions between pedestrians and autonomous vehicles. My mentor, Susan Ayaz, guided me through this process, and for that, I'm very grateful as she made the experience very interesting and I enjoyed it. So first, I think I should provide some background information on the topic. So if you're from like an urban area, you may notice the growing prevalence of autonomous vehicles. Like I'm from an area near San Francisco. So when I visit, I see a lot of driverless taxis, which could be categorized as a fully autonomous vehicle. So I thought that was very interesting. So specifically, we're seeing a rise in vehicle autonomy. And autonomous vehicle is a pretty ambiguous term. We might be talking about cars with cruise control or those that are partially automated. In order to categorize the level of vehicle autonomy in vehicles, the Society of Automotive Engineers contributes a well-recognized classification system ranging from level 0, no autonomy, to level 5, a fully automated vehicle. Here, we're referring to highly automated vehicles, which often refers to vehicles that are capable of driving themselves with little to no human intervention. Within the SAE system, this refers to vehicles operating at levels 4 and 5. As highly autonomous and often unmanned vehicles take on the road, it becomes necessary to maintain an effective route of communication between autonomous vehicles and pedestrians. Because pedestrians typically rely on eye contact, gestures, and body language from drivers to gauge intentions, the absence of such intuitive cues could create uncertainty about the vehicle's intentions. For example, if I were a pedestrian, I would be a bit confused about how I would cross the road if the autonomous vehicle was planning to stop or proceed. External human interfaces provide a solution to bridging this gap between human expectation and machine behavior. They must take on the role of clearly communicating the vehicle's intentions to pedestrians, especially during uncontrolled crossings. An EHMI may appear as a display on the autonomous vehicle that communicates the vehicle's states to surrounding road users. So you can see that in the middle image. Think of like dynamic light bars, the bottom image, auditory cues, for example, a human voice, pictograms, or even anthropomorphic or human eyes. Even though there has been significant progress in the field of each external human-machine interface development, there still remains a significant challenge of standardizing current systems. A lack of standardization has led to inconsistencies in how these signals are interpreted by pedestrians across different contexts. Many studies acknowledge cultural and demographic factors to play a role in how signals are understood, often noting limitations in participant diversity and education for smaller scale experiments. There are also gaps in creating EHMIs that are effective across different environments, as what works well in one setting may not be as effective in another. For instance, an EHMI using a flashing light to indicate the vehicle's intention to yield might be effective in a country where pedestrians are accustomed to waiting for explicit signals before crossing. However, in a different cultural context where pedestrians are more likely to assertively cross the street without waiting for a clear signal, the same EHMI might lead to confusion or hesitation, leading to reduction in its effectiveness. Such complications can limit the design process and make it difficult for regulatory bodies to ensure the safety of autonomous vehicles in dynamic urban settings. So the intended direction of my review was to provide a unified design framework for HMIs that prioritizes efficient interactions and the pedestrian's understanding of crossing cues. A quick overview of the process would be that I reviewed existing literature on external human-machine interfaces, focusing on the visual features, placement on vehicles, and the types of information or states displayed. I also used a consolidated search of relevant studies and an eligibility criteria for the inclusion of articles. Data is then extracted and analyzed to identify patterns and preferences that could inform a proposed HMI design. And here is where my methodology. So initially, 4 initial searches were conducted on Google Scholar using search strings composed of specific keywords and Boolean operators, which you can see below. And a multi-search approach was initially chosen to cover more ground by substituting terms with synonyms. Following several iterations of the preliminary searches, we concluded that a single consolidated search was sufficient for a small-scale review. So above, we have the final search string, which was conducted on August 1st of 2024, yielding 3,140 results, which was significantly larger than any of the other 4 strings. The search was pre-filtered to include only articles published from 2014 onwards to promote relevancy, and sorted by relevance. Abstracts were reviewed after excluding non-English articles, those from restricted access libraries, and those unavailable in full text. Due to the project timeline, only the first 100 articles were screened. Articles were then compared against eligibility criteria, which included specific rules for the exclusion and inclusion of articles. So here I wanted to insert like an embed of my chart, but I wasn't able to. So here's just a screenshot of a few cells. But this is what I did to exclude and include articles. So 20 articles were filtered through the eligibility criteria, and I chose 7 to include in my study. So I was looking for articles that first specified the level of vehicle autonomy and for highly autonomous vehicles, so those operating at an SAE level 4 to 5. I was looking for studies that focused on interactions between autonomous vehicles and pedestrians, studies that were road crossing specific, were in the perspective of pedestrians, and had a general focus group. So by this, I mean that if a study specifically focuses on how children perceive HMI cues, that would be a specific focus group. I'm also looking for studies that use relevant measurements and clear metrics. And here's another snippet of the specific information that I extracted from each included study. So I looked for a recommended design or the design types that were discussed, the information to be displayed, which could look like stopping, yielding, driving, the placement on the vehicle, the color of the HMI, and if there were surveys conducted within the study, what were the user preferences? So discussions and implications. So the 7 articles I covered included 2 video simulations, 2 framework developments, and 1 competitive evaluation, field study, and VR simulation. So for the study that proposes a taxonomy, it proposes an 18-item taxonomy to categorize 80 specific design features used in HMI implementations, such as different types of visual indicators or auditory signals. This was intentionally excluded when I tallied the design concepts mentioned, as it did not conduct a study or review that proposed a design. Instead, it served as a reference within my review to a broad collection of concepts and recommendations for HMI design. So here were the trends that I observed across the 6 studies, excluding the taxonomy. So out of the HMI types, the LED light strips and the text displays were the most prevalent and they were mentioned in 4 articles. 4 out of 6 studies provided color recommendations, with red, green, and blue each being mentioned 3 times. 5 out of 6 studies provided recommendations for HMI positioning. The windshield and grille positioning was mentioned 3 times. Vehicle intent and current driving actions were mentioned 4 and 5 times. So regarding the recommended states, I chose to divide them into 6 groups, which include the vehicle's intention, driving without yielding, yielding, resting, starting. Second, the current driving action, which is like speed, braking, turning, and it doesn't predict like an action in the future. 3, being automation mode, whether the vehicle is operating as an automated vehicle or being controlled by a driver. 4, the perception of surroundings. 5, crossing instructions and advice to pedestrians. 6, warnings, for example, danger zones or unexpected situations. And intention and current driving action can differ because vehicle intent refers to what the vehicle plans to do, while the latter refers to its immediate dynamics, such as speeding down or slowing up. These modes of communication often overlap and may depend on context, with some articles conflating current driving action with vehicle intention. So 4 out of 6 studies used surveys to gather participant feedback. Visual communication, particularly through color and text-based HMIs, was generally viewed as clear and effective, with symbols being praised for their intuitive and easily recognizable nature. Participants consistently emphasized the importance of visibility and the ease of understanding, favoring HMIs that were noticeable from a distance and straightforward to interpret. While text schemes were valued for their clarity, concerns were raised about their accessibility for vulnerable populations. Graphic and command schemes effectively captured attention and provided direct instructions, though they occasionally led to varied interpretations among different users. So, although the primary focus of my review was on the clarity of communication, it's important to discuss the potential loss of trust when prioritizing simplicity in EHMI design. For example, one of the studies examined 3 EHMI designs: anthropomorphic or human-appearing elements, infrastructure-based, and an LED system combined with text and graphic displays. The anthropomorphic and infrastructure-based EHMIs included auditory elements, while the LED system did not. The participants rated the LED system the highest for its clarity and understandability, yet it elicited lower levels of trust and confidence compared to the anthropomorphic and infrastructure-based designs. This can possibly represent a conflict in pedestrian preferences when interacting with autonomous vehicles. In contrast, the anthropomorphic EHMI was the most effective in reducing participants' hesitation when crossing. Such findings suggest that adding a human auditory component to LED and display-based EHMIs could enhance pedestrian confidence while preserving clear and explicit communication. Future EHMI testing should also consider both intuitive visual communication and the psychological comfort of users. And now I will present my proposal for future testing. So here is the process I took to design my HMI. The first picture is just a flowchart that you use to kind of draw out my ideas for the communicated states. If you can tell, unless the vehicle is at rest or displaying the countdown, an anthropomorphic speaker, a human voice, will announce the vehicle's current state. The color of the light strip will also depend on the current state of the interaction. And I designed a 3D model to show how the proposed HMI would appear in the vehicle. So my design uses LED light strips and text-based displays with anthropomorphic auditory component to promote accessibility and comprehensibility across different user groups. The LED light strips are placed along the vehicle's windshield, front grille, and back bumper. The display is positioned on the front grille and rear bumper, featuring white text on a black background to ensure clear visibility even from a distance. So this is what the coordination between the LED displays in the 6 states looks like on the actual vehicle. Some states use a combination of 2 message types. So resting combines driving action, like the vehicle is currently resting, with intent to continue resting. Cruising is intent, or it may come in the form of the vehicle not yielding, while pedestrian recognition is intent to yield and the perception of the pedestrian. Slowing down is the current driving action. It's not making any predictions. Cross safely is an instruction, and the countdown is actually an instruction. So I did have a few limitations in my study. So my review was conducted on a small scale, restricting the search to only open access articles and studies available through Google Scholar. The search was also not exhaustive, as only the first 100 articles were screened due to time constraints. The assessment of HMI effectiveness was often inferred from subjective measures such as trust and pedestrian comfort, which may have introduced biases in interpreting the results. Cultural and demographic factors were also acknowledged but not deeply analyzed within selected studies, limiting the ability to generalize findings across different populations. My study also relied on a limited number of methodologies, such as video simulations and VR simulations, with field studies being underrepresented. So this basically suggests that more empirical research is needed to support the design recommendations proposed. And some endnotes was that I had no experience doing a review or a scoping review prior to this. So I really enjoyed the process, and I was grateful that I got to look into how research is conducted, like how much you have to do and how to like write a scientific paper. So I'm glad that I had the opportunity. Thank you.